Welcome back. We are going to talk about hydrogenation. Hydrogenation just means putting hydrogens on alkanes. That's it. And if we have space, we'll talk about the diazomethane insertion. All right, let's look at syn additions to alkenes and specifically hydrogenation of alkenes. Let's take an example here. Here's an alkene. This just happens to be a cis-butene. You could also, do this with a trans-butene. It doesn't really matter. You need to have a very large atom, like a platinum, sometimes a palladium. You could even go with nickel, but turns out the more expensive the metal, the better the yield. Okay, so here's a platinum, and the platinum is a huge atom compared to hydrogen. So you take the platinum and then at very, very high pressures you put hydrogen on. So hydrogen will come sit on this and get absorbed. So the electrons are pulled towards that platinum. And so here is the hydrogen going over. And the same thing would happen to your alkene. It would get pulled over. And there would be a lot of these. I'm just drawing one or two. A lot of these. After it's absorbed on the surface, or while it's getting absorbed, then these then form bonds to the platinum. The platinum's got plenty of electrons, and it can also accept electrons. So this is just a platinum atom, and I'm just drawing these over here. Hydrogens growing like grass. And even your alkene is going to go over here. And more hydrogens. After they absorb, these electrons can actually migrate and move around. They can go find a hydrogen and bond to the hydrogen instead of the platinum. And these electrons can go into platinum. So the platinum can take electrons, give electrons. It's a huge atom. And so now we have one of the alkene termini hydrogenated. This bond here can migrate over to the hydrogen, and those electrons can go to platinum. Platinum, as I said, is a huge atom. There's a lot of give and take there. And so one of the alkene termini now picked up a hydrogen. And then the other one is still on. Now you can have, as I said, a lot of these hydrogen growing like grass on the platinum, completely covering the surface. Now these electrons can also step out and catch a hydrogen, and those electrons can go over here, and now you are released from that hold on the platinum. And in this case, well, really not forming a chiral center, you're just going to become butane. And this would be, depending on the metal, it could be anywhere 70 to 90%. Let's look at an example here for this. Let's take a cyclohexene, and let's say you have an ethyl and a methyl here. You put hydrogenated hydrogen under high pressure, platinum oxide for the surface, and you also have to cool it down and to minus 25 degrees C. You have a solvent here, ethanol. All of these you add to this, and you would have hydrogens going only on one side because it's controlled by literally the platinum. The platinum's holding on to it, so it can only go on the bottom surface of the alkene. Can't really go on top, right? You can see that it's not possible for this hydrogen to kind of jump over here. It is going in from the bottom and on the same side. Therefore, it's a syn addition. Let's say over here we have this, and your platinum is going to be on the bottom here, and you can either do it this way where you have hydrogens coming in, and it'll be the exact same mechanism. I'm not going to redraw it. Or you could have it flipped over, and you could have it going on the opposite side. So either this, or you could have it on the other side where you have this being your alkene. This can be flipped over horizontally 180 degrees, and you can add your hydrogens on this side, which means you're going to get two products here. one of them where you have your ethyl and your methyl up and hydrogens down. So this is definitely going to be cis. Or you could have a situation where you have your ethyl and methyl up in this direction and your hydrogens here. Now, are they both the same? Well, if you take this, you cannot superimpose it. If you flip it, then your groups are going to be down. They're not going to get superimposed. But you can see how you can reflect this on a mirror and get that. So you do get diastereomers, and you could have drawn them just like this as well, where your ethyl and methyl are up, plus where your ethyl and methyl are down. They're both mirror images, and you don't really have to put in the hydrogens, but since we put hydrogens on this reaction here, I'm going to draw them in, and this is going to be a 1-to-1 because there's an equal probability of going this way or flipped over on the other side. So you can go this pancake or the flipped over pancake, and you can get hydrogens on both sides. So that is going to be, this is exactly the same as this. So this is a 1-to-1 raceme. That means it is non-stereoselective. You don't get more of one or less of the other. So it's non-stereoselective. It's non-regiospecific. That means the hydrogen doesn't choose to go here or here. It has no choice. It has to go on both ends. So it's non-regioselective, but it is stereospecific because they go on the same side. It's syn stereospecific. And hydrogenation is a huge industry. You take these long chain unsaturated oils, and then you put nickel and hydrogen, hydrogenate them, and then they become solid. And so because you know they are now alkanes, then you can't believe it's butter. You spread them on and they taste really good. So this is an example of hydrogenation. It's syn stereospecific, non-regioselective and non-stereoselective. Let's look at another one since we have space here, and that's going to be a diazomethane. Let's look at this diazomethane reaction with alkenes. This is a solvent diethyl ether. Diazomethane is a very toxic, yellow color gas, which is extremely bad for your lungs. So you kind of take this and use it really carefully. It can be explosive too. And you have heat or light, and that is then going to go in and insert. Let's look at the mechanism, shall we? So if you take diazomethane, you have 2 hydrogens on that carbon, and if you do the Lewis structure, you would have a nitrogen here and this, and you have only 3 things in here. You also have a lone pair. So if you take the formal charge, it's going to be 4 minus 5, 1, 2, 3, 4, 5. That's going to be a -1. So this is a minus. Well, you can have, resonance to this as well. But when you hit this with light or heat, it's going to then go over and form nitrogen gas. And it would do that effortlessly because nitrogen gas is the most stable gas on the planet and saving us from the sun. And here is your carbon, which is now called carbene. You have a lone pair here. So you have a lone pair here and 2 hydrogens. It's going to be sp2. Then you also have an empty p orbital. So this has got a lone pair and an empty p orbital. This is a carbene. These are extremely reactive. And so this would just go catch any nucleophile it can, and the one that's over here is a nice alkene. So your alkene electrons here see this as an empty orbital, even though, you know, it's a neutral formal charge now. This is not a positive. If you do the formal charge, it's 1, 2, 3, 4. 4 minus 4 is a 0. So it's really not charged. It's neutral. However, because you have a empty orbital, this can function as an electrophile. And you have a filled orbital that can function as a nucleophile. So it's got, you know, a bimodal reaction here. So this is going to go in here, make a bond there, and this would come over here. And this happens at the same time. You don't have a stepwise reaction here. And your nitrogen goes off into the atmosphere, leaving this little thing here to go on top of the alkene. So you have your carbon forming a forming a triangle right on top of that. Now this is going to be syn stereospecific. You don't really have a choice here, because as this goes over here, this comes at the same time. There is no place where it's just holding on to one and rotating over there. There's no rotation. So this is breaking up, and this is forming all at the same time. So that is a transition state. When all is said and done, you are going to get a nice insertion here, and it's going to be either on this side, and you will have your hydrogens going in, and you're going to get that. So they form this cis diethyl cyclopropane, and about 70% yield. Okay, you could also have, as I said, the other one, and it's going to be the exact same molecule. Now, if you had different groups on it, it would be different. Well, I'm just going to draw the other one just to show you it's the same. So you can either also have the groups go in, and hydrogen's coming out here, and you can have your cyclopropane going above. All right. Again, these are the hydrogens that came over with your carbene. You can have other R groups here as well. These two are exactly the same. However, if you didn't have a symmetric alkene, let's say you started with a trans, then you would get a trans. So their stereochemistry is preserved because it's a syn stereospecific reaction. It's going to go on both ends equally, so it's non-regioselective. And there is no choice about this carbon more than this carbon, so it's non-stereoselective as well. So this is a very stereospecific reaction, syn stereospecific. Let's look at an example of, let's say, a trans, because we already did a cis. Let's do a trans. Let's say this is a trans, and it's not symmetric. Let's take a look at this. What is this going to give us? It's the same conditions as before. Let's say we add to this a carbene. We could have other ways of making carbenes like chloroform and potassium hydroxide and so on, or heat or light. You can get carbene insertion from above or below. And let's see what those two are going to give us. So over here, you can have your this out and this in, and same on this side, hydrogen out and methyl in. And here's your methyl group here, and your carbene can go on the top. Or your carbene can go on the bottom. So you can have this go the other way on the carbene. If that happens and the carbene comes from the bottom, you would have this with this going out, and you would have the hydrogen go out and the methyl come out, and you would have your cyclopropene pyramid over there. All right, well, what's the relationship between these two? If I take this and rotate it, I still won't be able to superimpose on that because we have different groups. However, if I keep a mirror here, it's going to reflect exactly this molecule. So you can see they are going to be enantiomers. So these two are going to be a 1-to-1 raceme. they're both enantiomers. So depending on your starting material, you can get different products. So you can get different symmetries in your product. But through it all, your reaction is going to have the same exact stereospecificity, and that is syn. And that's the most important thing here. You're going to get a syn stereospecific addition onto an alkene. Alright guys, I think we've pretty much covered all of this. This HBr peroxide is going to put your HBr anti-Marconic up, and we are going to do that when we talk about radicals. So we pretty much did the entire board here. All of these reactions are done with mechanisms and examples. Let's go in and put them all on the same page and see how they compare and what they do. So we're going to do a wheel of reactions. Can't wait for that. But before that, make sure you know the stereochemical outcome for each of those reactions. And that would be pretty much obvious only if you know the mechanism. So don't try to memorize it. Think through it with the mechanism. Come up with your stereochemistry and your regiochemistry first. Then we can do all of those reactions. If you have any questions, you know who to ask. Talk to you soon. Bye.